everyone. Thank you for coming to this talk. I'm going to be giving you all an introduction to Qiskit and IBM Quantum in this code workshop. I have the Jupyter Notebook available at this link here, which I will drop into the chat right now. So if you want to kind of go along and download the notebook and follow along while I talk, please go ahead and do that. There are some instructions at the top of the notebook about how to download it. And if you want, what I'm currently doing is I'm running it in the IBM Quantum lab. So it gives you some instructions there for how you can upload your notebook and get it going within the IBM Quantum kind of lab environment, which is quite a nice way to do things. So you don't have to worry about setting up your own Python environment and things like that. So what am I going to cover in this talk today? I am going to try and cover quite a lot of things. If you are very, very new to quantum, some stuff might be a bit too advanced for you. Similarly, if you are maybe more into very advanced subject matter and you are a researcher, maybe, I'm not going to be able to tell you how to make novel breakthroughs in your own research. But really what my goal is here is to essentially show you the toolbox that is available to you, no matter what stage of your quantum journey you are at, whether you're just getting started with quantum circuits, whether you're already doing research and wanting to do real experiments on real hardware. Hopefully there should be something in this talk for you. We're going to try and cover a lot of stuff. Don't worry if you aren't following or keeping up. The notebook is all there with all of the code already filled out for you. So I would say don't stress too much about following every little detail, but just try to get a general kind of feeling for the concepts that I'm talking about, and then go back and look at the notebook later to get a little bit more of an in-depth understanding. I'm just going to start off talking a little about me, and we're going to show you the kind of IBM Quantum website and what cool things you can do there. Then I'm going to give you a high-level overview of what Qiskit is and the broader Qiskit ecosystem. And then we're going to actually dive into some code, starting with representing quantum states using Qiskit, then running it on devices, simulators, and some real hardware, how you can visualize your results. Then I'm going to touch on some slightly newer features, specifically IBM's Qiskit runtime and the Qiskit primitives that enables that within Qiskit. And then lastly, I want to talk about a couple of our applications modules, particularly our low-level applications. Probably Qiskit experiments and Qiskit dynamics are the ones we'll focus on. And yeah, we'll see how far we get through this. I might not be able to cover it all, but luckily you have the notebook and you can finish off at home if we don't manage to cover everything within the hour. So starting off just a little bit about me. My name is Abby. I am a quantum developer advocate. I joined IBM in 2019 as a web developer before moving into the quantum department and becoming a developer advocate. There are some links here if you want to kind of get in touch with me on LinkedIn or see what I'm doing on GitHub or social media, follow new things that are happening in Qiskit, please go ahead. Yeah, okay, enough about me. Let's talk about quantum. First up, I actually just want to talk a little bit about this platform that I am going to be running this notebook in today. I'm just coding in a Jupyter Notebook right now, but what I'm actually running it in is this IBM Quantum lab. But I might actually just go to our home page. WebEx is in the way. So this is kind of the main page of your IBM Quantum account. You can log in with, most types of email IDs work. And there are a couple of cool things here that I just want to highlight. The first one is the Quantum Composer feature, which specifically for people that are pretty new to quantum, if you want to play around with putting circuits together, visualizing what those outputs are going to be, seeing how that translates into OpenChasm code, this is a really nice little playground for you. Also, maybe if you are a teacher or a lecturer and you want to create a nice visualization of what you're doing and you can't be bothered to generate your circuit with code, you can just drag and drop some things, take a screenshot. It's a nice image that you can stick in one of your lecture slides. Next up, we have the compute resources that I want to speak to you about. This is if you want to run anything on IBM Quantum devices, you can see a full outline here of what is available to you. You can kind of see all of the different systems that are IBM currently has and different metrics around them. And they also have some information about simulators as well. So this is a really nice tool if you, I don't know, can't remember how many qubits, IBM Montreal has, then you can like quickly look this up. It's just a nice reference point to have. And then the last thing is this Jupyter Lab environment that I'm going to be running this notebook in. You can upload any Jupyter notebook to this, and it has a nice just Python environment all set up for you, just like you would run a normal Jupyter notebook. But you don't need to do as many of the installation steps. It kind of installs quite a lot of the IBM provider stuff for you. Yeah, so that's just a nice kind of overview of what's available to you. I really encourage you to go have a play around with that, upload your notebook into this environment, and you can kind of edit it and change it and use some of the cool features here. Okay, now let's talk about Qiskit. I think I can just about see this diagram within the zoomed in layer that I have. Okay, so this is an overview of really Qiskit and the Qiskit ecosystem. There are many different packages that kind of make up the Qiskit ecosystem, all kind of surrounding the main Qiskit package, which is kind of in a development stage, is known as Qiskit Terra, which is the main package that you're going to use to build quantum circuits, interact with real devices or simulators, and that is the main package that we're going to be spending the most of our time with today. And then you have quite a few other packages kind of surrounding Qiskit that we say we call them part of our ecosystem. We have high-level applications here. These are packages that maybe focus on a particular industry application of quantum computing, and they will use Qiskit, but also have some extra, functionality on top of that. So Qiskit Nature is all about doing quantum chemistry applications. Qiskit Finance, as the name suggests, is all about financial problems that we could potentially solve with quantum computers at some point. Optimization is for optimization problems, like quadratics and things like that. And Qiskit Machine Learning is looking at quantum applications in the machine learning space. So if you are interested in investigating any of those applications of quantum computing and you are kind of familiar with Qiskit and you want to use some extra nice kind of features and functionality, I recommend going and checking out some of these extra projects. And then we have the low-level applications. So this is normally talking about stuff which is probably like a little bit closer to the hardware. Qiskit Metal specifically allows you to kind of render how to kind of do chip development, for real devices. Dynamics is all about kind of modeling quantum systems at kind of like a Hamiltonian wave level. And Qiskit Experiments is about, doing a lot of experiments on hardware, looking specifically at things like benchmarking, different types of ways to measure error rates on gates, for example, that kind of thing. And then we have Qiskit itself, which kind of forms the core of the everything that's kind of around it. And we also have here, I want to talk about devices. Simulators, specifically Qiskit Air, is probably one of the best ones out there. This can simulate quantum results up to kind of a certain number of qubits. Obviously, it can't do as much as real devices, but it can help for much smaller problems. And then we get into the realm of hardware providers. So these are a whole range of different providers of quantum hardware that you can use Qiskit to run, your experiments on. So obviously IBM has a bunch of backends that we can use Qiskit to run our circuits on, but there's plenty of other ones that Qiskit can plug into pretty easily, like IonQ, AWS as well. There's a whole bunch of different ones there. Another way of thinking about the ecosystem, I might just have to zoom out a little bit for 1 second to fit this on the screen. Well, it doesn't work very well, but you can kind of think of the ecosystem as all these rings around Qiskit Terra. Qiskit forms the nucleus of this kind of sphere, and then surrounding it are different members of our Qiskit ecosystem. And within the ecosystem, there are kind of different levels of project. Ones that form the main tier are the ones that are the most closely affiliated with Qiskit itself and have the most support from IBM. The extensions tier also has, pretty good interaction with Qiskit, but isn't as close to us. And then the most interesting one, I think, for this audience is the community tier. And this is really for us to help support any other members of the broader ecosystem who want to, who want to build on top of Qiskit, expand Qiskit. Maybe, you have a project or a feature that isn't appropriate to have merged into the core Qiskit module itself, but is still providing value. And if you open source it yourself, you can apply to join the ecosystem and join this community tier. And I think I've added the link here. If you go to the qiskit.org/ecosystem link, zoom in again. If you go to qiskit.org/ecosystem, then you can follow the information there about what kind of projects join the ecosystem, what you need to do to get your project to a good enough state to apply. And yeah, there's plenty of information there. And I really encourage anyone who is passionate about open source, who has developed their own project. And yeah, I recommend you applying to join the ecosystem. Okay, time for some code, finally. First off, we are just going to start with some imports here that we're going to probably need at some point. Don't have to worry too much about what's going on here. We need to import the visualization module, the air PASM simulator for the providers. These are pretty much standard imports that you'll probably see in a lot of demonstrations, pretty good ones to have. The specific Qiskit submodules that we're going to be touching on, I've just listed here. This is a very condensed version of, there's a lot of modules within Qiskit. I've just picked, a few highlights to show here. Definitely go and have a look at some of the other ones though. This is not the full spectrum of everything that you could do, just highlighting a few specifics. Okay, let's get started with how can we, prepare quantum states using Qiskit. The first way is probably the most classic way, probably the one that you're the most familiar with if you're already a little bit involved with quantum computing, and that is creating a quantum circuit. Doing this in Qiskit is very simple. Firstly, we're importing quantum circuit here from Qiskit, and I'm just going to create a Bell state here. So this is the simplest example of entanglement in quantum computing. And to do this, I've initialized a quantum circuit here with 2 qubits. That's the first number that I've passed there as an argument. So then now that I've initialized this quantum circuit, then I need to apply my quantum gates. So the first one I'm going to apply is a Hadamard on the first qubit, qubit 0. And then I'm going to apply a controlled NOT gate with the control being on qubit 0 and the target being on qubit 1. And then I'm going to measure the states. And if I just print out my circuit, this is kind of what it looks like. I'm sort of assuming that most of you already know this or are aware of the quantum circuit concept. If not, there's plenty of resources out there to kind of catch up with that information. But this is kind of just a very simple example of how to implement it within Qiskit itself. But once you start doing more complicated things, you maybe want to expand what you're doing beyond just the basic gates that Qiskit has available. So maybe you want to start doing some custom rotations. So then what you can do is you can add a U gate to a circuit. So here I've just created another quantum circuit, this time just with 1 qubit. And I want to create a general rotation with some pi/2 values. And to do that, I'm using the U gate and then passing the rotation values that I want to each to the U function there. And then the last argument here is which qubit I want to apply that gate on. And that, as you can see, creates a U gate with 3 parameters, each of pi/2, and I've applied it on that 1 qubit that we have in our quantum circuit. As we go along, by the way, I'm not going to stop for questions until the very end, just because we have a lot to get through with time, but feel free to drop your questions in the WebEx chat, and we can come back to them at the end. Yes. Another thing that you might want to do is deal with matrices. And then you'll want to convert that to a unitary gate that you can then apply to your quantum circuit. And yes, you can do this in Qiskit. So here I've just created a matrix from a Python kind of nested list. I've initialized a quantum circuit object, and then I've called this unitary function, which essentially applies a unitary gate based on the matrix that I provided. And I specified which qubits that I want to apply that on. This is a 4x4 matrix, so that's going to be a 2 qubit gate. So that's what this is going to create for me. And this maybe doesn't look very nice. Like maybe you want to see what actual gates it ended up creating based on this matrix. But Qiskit has tried to kind of make things simple by kind of just covering this in a general unitary kind of box. But if I want to see what's going on underneath the hood, I can call this decompose function, which is a super useful function when you're working with Qiskit and you're building circuits and you're not sure what's what anymore. You can always just call decompose to kind of see what is the basic gates that are being used for your circuit. If I run that, I can see I have a couple of U gates with different rotations and a CX gate as well. Another way to prepare quantum states for Qiskit is you can use the state preparation class or the prepare state function. There's a few different ways that you can call this, a few different types of argument that you can pass to this. You can just pass an integer value, you can pass a matrix, or you can pass a bit string. All of those will kind of work in the same way. And we'll end up with this, again, a box that says state preparation, but you can, again, decompose that to see what's actually going on under the hood. So this is just another nice tool for preparing a quantum state, depending on what you're wanting to play around with. And this is I think one of the really cool things about Qiskit is we really try to give you as many different ways to do things as you want, so you can kind of adapt you don't have to change up your workflow too much. We give you lots of options to however you want to prepare your quantum state, we'll try and accommodate kind of idea. Next up, we have parametric circuits. These are really great for variational algorithms if you're familiar with BQE. So you have a gate, you have particular rotations that you want to do, but you want to test out different types of parameter values each time, like a different rotation each time you run the circuit. And you can do that quite simply using Qiskit. The first thing that I'm going to do is create this parameter class, and I'm just going to give my parameter a name theta. Doesn't really matter at this point what that is. I'm going to create my quantum circuit, and then I'm going to apply a rotation gate. Here I've just chosen an RX gate, and I'm going to pass that parameter class that I've just created there. Normally, what I would have, an example that I kind of showed earlier was you might, put a specific value like pi/2 there, but we want to be able to change this value around later. So I'm using this parameter class here instead. And I'm saying which qubit I want to apply it on. And here, instead of having like pi/2 be the value, I have theta, which is kind of like a placeholder for the moment. But then let's say at a certain point, I want to actually replace that theta with a real value. So in this case, I just want to replace it with pi. Then what I can do is call this bind parameters function on my quantum circuit, and then say, okay, I want to change out this theta variable with the real value that I want. And in this case, I've just used one value here. But in the case of like variational algorithms, you know, when you're replaying the same circuit many times, you can pass like a list of values here. So you say each time I run this circuit, I'm going to use a different, I'm going to kind of iterate through that list of values to you know, try out different ones. Next up, I want to talk about control flow operations. This is a somewhat newer feature within Qiskit for those that want to do kind of conditional programming with quantum circuits. We had some type of control flow operations in previous versions. We had kind of this very simple C-if functionality, but this is now changed. We have a different way. So I'm not even going to touch on this old way too much. I'm just going to focus on the new way. So basically what control flow is within quantum computing, if you don't know already, is you can have a circuit that is running, and then maybe you want to do a measurement in the middle of your circuit, and then based on the results of what you measured, then you want to make a change to that same qubit. And up until very recently, that hasn't really been possible, but now kind of quantum computers are getting to the stage where this kind of thing is almost there, or we're starting to be able to have qubits that have a long enough coherence time that we can start doing this. And so Qiskit is really keen to implement this kind of functionality as early on as we can, so that when we have, you know, really good control flow capabilities on the hardware, the software doesn't become the bottleneck or the blocking factor. So you can actually use a lot of control flow operations already that aren't, you know, even fully available on hardware, that you can simulate with Qiskit, which I think is pretty cool. So this example here is how do you do a basic kind of if statement with Qiskit. And we try to follow regular Python kind of if-else statements. You know, sort of. So here I've just started off, I've created a quantum circuit, added a Hadamard, I've measured it. And then what this little block of code here is doing is it's saying, if I measure a value of 1 on qubit 0, then what I'm going to do is reset that qubit and add an X gate to it, and then measure. But if I don't measure that 1 on qubit 0, then this code won't execute. So if I draw it out, this is kind of what it looks like. We don't have a great way to visualize this at the moment in this matplotlib drawer, but that's possibly something that's going to get better over time. And if I was going to run this on real hardware, we're going to talk about that later, you would be able to see that your final results here would change depending on what gets measured after this one. So would it apply that X gate or would it not? Another thing that you can do with control flow is a while loop. So this kind of, I have the same kind of basic setup here for my quantum circuit. But this time what I'm saying is keep measuring my my qubit 0 and until I measure a value of 1 and then stop the loop. This is kind of how you can see how classical Pythonic programming we're trying to sort of replicate logically with Qiskit. And yeah, we still have a lot more things we can implement in this space, but it's kind of exciting that we already have some features that are available here for this. All right, next up I want to talk about quantum info. This is a really important module in Qiskit if you are doing, I think, any form of research or kind of more advanced things, and you want to do more kind of mathematical operations when you're dealing more with like operators rather than at like the gate level. The kind of classes I'm going to talk about specifically here are operator and Pauli. The first one operator basically lets you kind of input any matrix and it will kind of create an object for you, which, oh, I need to actually import it first. One step. Yeah, so it will kind of create this, in this case, I've just put in a big NumPy list, and it's kind of created this matrix operator object for me with the real and the complex parts. And you can, this is a very interesting class because you can kind of convert it into a lot of other classes within Qiskit, whether it's a Pauli class or a gate or an instruction or a whole quantum circuit. So for example, I could create the same gate that I just did here, which is like a double X gate, maybe if you're operation, if you're familiar with that. I can do the same thing with using the Pauli class as well, just by passing in capital X here. And it will, and then I can convert it to an operator as well. So yeah, here I've created exactly the same thing as I created up here, but I've just gone about it in a different way. So like coming back to that concept of like Qiskit tries to give you a lot of different things to do the same thing to, you know, whatever kind of fits your style of working. So this Pauli class has all of the Pauli, the common Pauli matrices available to you, the X's, the Y's, the Z's, identities, etc. There's also Clifford gates as well that are available in this quantum info. I could go on forever about this module, but I'm gonna move on quickly. Another example is you can take, Qiskit has these gate classes. So this is an example of how you can convert a gate to an operator object just by passing it directly into that, like that. And lastly, like for example, you could create a really long circuit like this, and maybe you need this in matrix form. You can convert it to an operator just by, you know, creating your circuit and then passing that circuit to the operator class, and then bam, you have this really long object, this massive matrix, which is equivalent to that circuit that I just showed you. You can also do a whole bunch of kind of mathematical operations on them, which is, you know, why would you bother creating these operator classes in the first place? Because you have a lot of other nice Python functions that you can do with it. You can use a lot of the Python maths functions as well as some built-in ones as well, like tensor products, for example. So here I've just created an operator from a Pauli X class, and then another operator from a Pauli Y class, and then I just got a tensor product of the two. And you can do the same with compose, and I really recommend going and looking at the documentation for this a little bit more and seeing what other maths operations that you can do. There's quite a lot. And here, let's say you've created an operator, but I actually want to add this operator to an existing quantum circuit that I had. You can do that as well. So here, again, I've created an operator. I've just passed in a Pauli that I was starting off with, and I just called it XX. And then I created a quantum circuit. And then I want to add this operator to that quantum circuit that I added. And I can do that with the append function. And this is something that you can do with all quantum gates in Qiskit, and the operator also works with that function as well. I just say what I want to append to my circuit, which qubits I want to apply it to, and then Qiskit does its thing and it applies it. Yeah, and I can also just call it directly within there. It's just a little maybe Python trick. I don't have to go through the whole rigmarole of declaring it here and then passing it. I can just go straight for the Pauli operation through there as well. Like that, pretty easy. Okay, now we've shown you a whole bunch of different ways that you can create your quantum state and your quantum circuit with Qiskit. Now let's actually kind of run them and see what kind of results we can get. So first up, I mentioned Qiskit Air is it's a simulator that you can use to simulate small circuits. So we're just going to list out what are the different types of backends that are available on this simulator. We have a whole bunch of different things here, depending on what specifically you want to do, what kind of results you want to get. we're just going to use the kind of the basic one, the air simulator, for this demonstration. But yeah, go ahead and try out these other ones if you're doing more kind of complex things in your own time. Just a reminder, we created our Bell state earlier. So how would we actually run this on a simulator? The first thing we're going to do is we're going to initialize our simulator object. To do this, we're going to call air.getBackend, and we're just going to use the air simulator here. But instead of air simulator, you could, for example, take any one of these here and use that, and it should work. And then the next step is really important. We're going to transpile it. I don't have enough time today to talk to you about transpilation, but this is an important step for kind of reconfiguring your circuit into a different circuit that is optimized for the particular backend that you're running it on. It's super important for when you're running it on real hardware. I think it's probably not as important if you're running it on a simulator, but I like to show that step anyway, because I think it's good practice to transpile for your simulator, then you remember to do it when you're running it on real hardware. So I'm going to call transpile. I'm passing in my Bell circuit, and I'm passing in my simulator, and then I'm just saving that in this Bell circ object. Now to actually run it, I'm just going to call simulator.run, pass in my Bell circuit, and I want to get the results back from running this circuit, and to do that I just call .result. And then result is actually gives you a really big object with lots of data in it. And specifically what I'm looking for is I want to get the counts data back. So to do that, I'm going to call get counts, and then I have to pass in the Bell circuit again. And then if I print my result, you can see, as you would expect from a Bell circuit, you get a perfect split of, 50% of the time you're getting 0, 0, 50% of the time you're getting 1, 1. If I wanted to break that down and say I want to get a result for every single shot, I can add some more some more arguments to this run function. I can say I specifically want to run this circuit 10 times on my backend, and I want to see the result for everything for every time that I run it. So I'm going to set memory equals true here, and then the rest of it is the same. I call .result, and then this time I want to say when I've got my result, instead of getting counts, I want to get memory. Then if I print my results out, here I have 10 different times that I've run the circuit and the 10 different results that I got. This is particularly useful if you want to do any kind of like advanced data visualization afterwards and you need, the exact results. And the results that I've just done here is with a simulator in like a perfect simulation of what the results would be. But sometimes you don't want to see what the perfect outcome is. You want to see what the outcome would be if you simulate your circuit on a noisy backend. So you can actually add some artificial noise into your simulator to kind of see what that would look like. And Qiskit is cool because Qiskit is cool anyway, but it's particularly cool because with the air simulator, you can also use some fake providers, so some fake backends that are based on real IBM hardware. So for example, IBM has a Bell device, and I want to kind of simulate how much noise I would get running a Bell circuit on this device. So I can use this fake Bell which has similar noise profile to the real device itself. And then I can get some results from that. So to do this, what I have to do is import the fake device from fake provider. And this time I'm calling, when I'm getting my backend, I'm calling the air simulator, calling from backend, and then passing in this case, fake Bell. Transpiling, as we already discussed, and then running and getting results and getting counts is all the same. And then if I print out my results, I can see here, I've just compared for the moment what I got when I was just running it on the basic air simulator, giving the perfect output. And then this one is what I got from running it on that fake Belém simulator. So you can see here we're getting now some noise, that's some artificial noise that's been added. You can also get things like your state vector results. If when you've created your circuit, if you say save state vector, if you call that function, then what you can do once you've run it on your simulator, got your results, then from the result, like we did get counts and we did get memory, you can call get state vector, and that will get you a nice, I formatted it here nicely with this array to latex function, but you can get some state vector output from your results as well. And you can also get some a unitary matrix output as well if you use save unitary, and then run it like you normally would, and then call get unitary at the end. Then you can get your unitary matrix output as well. So yeah, a lot of different ways that you can run your circuits on simulators, a lot of different types of data that you can get back. I really encourage going and looking at the documentation as well to kind of dig through and find some treasures that maybe you don't get from your average tutorial or talk like this. I'm trying to highlight here specific things that, you know, maybe you do already know, maybe you don't already know, some of the more kind of hidden gems of the SDK, because there really is so many tools in this toolbox, and most people maybe don't uncover the full kind of breadth of what is available. Okay, now some real hardware. Because we're running this in IBM Quantum Lab, and we are being hosted by IBM today, we are going to focus on how do we run these circuits on some IBM hardware. Qiskit has a nice little tool, Jupyter visualization tool here called Qiskit Backend Overview, which you can run in your Jupyter notebook, and you can run this locally as well. And this kind of prints out a really nice little real-time dashboard for you of, I think it's all the free systems that are available. And it kind of gives you a bit of the stats that I showed you earlier. And also it gives you some information about how busy that device is and how long the queue is for a given backend, which is really helpful because the free ones, because they're free, sometimes the queues can get quite long. So choosing what device you want to run your small things on the free ones is really helpful to have this information. Another way that you can do this directly is by calling this least busy function from the kind of the IBM Q provider provides this information for you. So to kind of retrieve the least busy device from IBM, I'm calling this less busy function, and then I'm calling provider.backends, and I'm passing in some filters about the kind of backend that I want. So I want it to be a real backend. I don't want it to send me a simulator. And this little lambda function here is basically just saying, I need a device that has more than or equal to or more than 2 qubits. So I don't want a 1 qubit device. I don't think there even is any 1 qubit devices anymore. But you could like raise this number to however many qubits that you actually need for your experiment. So here, if I call least busy device, it will tell me, give it a minute. IBM Q Manila is currently the one with the shortest queue and what I'm most likely to get the quickest results from. And this little widget gives you much more information as well than the other one did. Like all of this, I don't even know what that is. I'm not a physicist. Yeah, it gives you so much information here, all just with like a couple of lines of code, and you have all the information that you need. I'm not going to actually run this on a real device for you right now because with Jupyter Notebooks, that means that I wouldn't be able to run any of the later cells, and then we'd be kind of waiting around for a while. But I have just left the code here for those of you that want to try this at home in your own time. And the way that you run on a real device is very similar to the way that you run on a simulator. You have to get your device, transpile for it, run the circuit, get the results, get the counts. And what you can also do if you do this within IBM Quantum Lab is you can see, if you open, I think it's this tab. Yes, you can see here any jobs that you have run and what their status is, if they're kind of being queued, if they're completed, etc. So it's a nice little additional kind of login here for you. If you have kind of your own special group within IBM and you have special access to some of the more paid devices, you need to kind of specify a few more details when you are getting access to that. When you're fetching your backend, what you need to do is you just specify, when you specify your provider, what your hub group name and project name is. And for me, it's what's nice with doing things in the Quantum Lab environment is that all of my credentials, my API key and stuff is already kind of been set up for me because I've logged into my account and I don't need to do any of that. But if you don't do it in the lab system, then you need to make sure that you're kind of loading your API keys properly. And lastly, Qiskit is backend agnostic. So I focused on IBM devices here, but Qiskit also lets you run things on plenty of other backends. For example, here I've just left you a nice little code snippet for how you do it for an IonQ provider. They pretty much all run quite similarly. We try to kind of make things as consistent as possible. So you have to initialize your provider. In this case, it's IonQ. You need to create your backend instance by calling provider.getBackend and then putting the name of the device. Then you do backend.run, and then you get your result, and then you get your counts. How are we doing for time? Ooh, okay. All right, let's try to speed through some things. Next up, we have visualizations. You kind of saw a little bit of them already, but Qiskit has some nice visualization functions. So this draw function lets you draw out your circuit. But a cool thing that you might not know is that you can change the style of the output by specifying output, and then there's a few different options that you can pass. So for example, if you want to draw a circuit in latex form that you want to use in, for some academic purpose, then you can do that. This gives you, give it a minute. There we go. This gives you kind of a latex image version, which is quite nice. And you can also just do a basic text version if you don't want the brightly colored matplotlib style. For all of the counts that we gathered up earlier, we just printed them out, in quite a boring way. We just kind of gave you like just some data like that. That's not very pretty, but if you use the Qiskit, if you use Qiskit, it has a bunch of different graphing functions for you. So here I'm just using plot histogram, and I'm saying I want to include counts and the noisy counts that we got earlier. So then I can see here, this is kind of the difference I can see in the results from what I got on the perfect simulator is in blue, and then the noisy simulator in pink here, printed out in a nice graph. And there's a bunch of other different graphs that you can do. Go and look at the documentation. Also, most of these visualization plotting functions are based on kind of matplotlib functionality, which means there's a lot of like common Ooh. All right. There's a lot of common matplotlib, if you're familiar with that. Package is very powerful Python graphing library. And there's quite a few different types of things that you can do to make your graphs look pretty, basically. I'm not going to spend too much time on it. You can look at this a little bit later. There's other cool things you can do, like coupling maps. You can create your own kind of layout for a device. I'm just really like going through this quickly now. You can also, okay, this one is quite cool. So you can say, okay, I have a backend, but I want to see what the circuit layout structure is of a certain IBM backend. So you can do that by doing plot circuit layout, passing in the backend that you, the circuit that you want to plot onto that backend, and then the backend itself. And this will kind of show you, okay, so if I was going to run my Bell circuit on this Bell-M backend, this is how my qubits would actually end up getting laid out on the machine. That's really helpful if you're doing any of that kind of low-level work. You can convert your circuit to a DAG, which is just a different way of structuring your, you know, what your circuit basically looks like under the hood in terms of kind of I guess like a logical map of how it works. Okay, how are we doing for time? 10 more minutes. I want to spend 5 minutes just to talk about primitives because it's quite a new feature within Qiskit, and I think it's quite an important one. So I think this will be kind of the last concept that I talk about in detail. But essentially everything that I've shown you how to run stuff on simulators and on hardware so far have been following this circuit execution model, which is very much you create your circuit, you send it through to the IBM devices, it sits in a queue, it runs, and you get the result back. And I didn't even run that because the queue was so long, and I knew it would take some time to get results back. Here, for example, and you can imagine if you're doing something like VQE, where you need to run loads and loads of different circuits many times, then the wait time can get astronomical because each time you're sending a new circuit to go run on a device, it gets added to the queue and you have to wait each time to get through the queue to get your result back. So this quickly becomes very unscalable when you only have a few amount of devices and many people that want to run things on them. So IBM has been kind of experimenting over the last few years with different ways of improving this process. Maybe some of you remember the first kind of version of runtime was runtime programs. And what this was specific, for example, VQE programs that lived within the IBM servers, within the IBM Quantum kind of cloud infrastructure. And what you would do as a user is you would say, I just want to run a VQE. And then that would kind of, you would just send that one VQE object to the queue, it would run it, and you would get your results. The problem with this was you lost some of the flexibility that you had with just, you know, being able to create your circuits yourself and do a lot. It was a lot more configurable on your end. So each of these had different trade-offs, right? These two methods, doing things locally or doing them with runtime programs. So that is why this newest kind of version of runtime is we're trying to go for more of this module. So kind of like giving you a little bit more control here, but also kind of just having you send one thing to the queue to have run and execute. And so that's where this kind of primitives execution model comes in, which is essentially you open up a session, which is essentially a connection between your computer and the quantum device. You have one thing in the queue, and then you use primitives, a primitive execution model within your session to execute your circuits, and you have a lot more control on your end of what you're doing. So if we just kind of compare the different trade-offs here, the runtime primitives module gives us the flexibility that we wanted, and it kind of helps reduce the queue time, and it also comes with extra things that we can do on the IBM side to make your results better. For example, like built-in error mitigation and things like that previously was much more difficult and you had to configure a lot on your end. So to be able to do this, Qiskit had to adapt a lot of its stack to support these primitives. And so that's where Qiskit came up with their primitives that kind of interact with the IBM primitives. So we have the Qiskit sampler and the Qiskit estimator. The sampler primitive is for getting counts back, so running your Bell state, getting your counts. Estimator is when you're doing maybe more like VQE type algorithms and you're trying to estimate an expectation value. Those are the two primitives that are available right now. There might be more in future, but that's what we have to work with at the moment. So firstly, I'll just show you how to run those things within Qiskit. If you just use the Qiskit sampler, then you're essentially using a simulator under the hood. So for this, what I'm doing is I'm importing the sampler object, calling sampler, I'm saying how many shots I want, and then I'm doing sampler.run with my bell state that I had before, printing my results. So far, very simple, like very similar way of doing this is just running on a regular backend. I'm just calling this extra sampler class instead of, you know, get backend, blah, blah, blah. And then doing things for estimator is kind of similar. I'm not going to talk in too much detail here, but maybe you're familiar with, you know, this kind of type of doing like a variational algorithm. So here I'm just creating an ansatz for my random algorithm, and I want to estimate what the expectation value would be from this. So to do that, I'm calling my estimator primitive, calling estimator.run, and then I'm passing in my ansatz, my observables, and my values. Don't worry if what I'm saying is going over your head. Just look at the code later. But this is kind of the basic process of how you run it. And this just is giving us a result. Don't need to worry about that too much. It's more the concept that I'm trying to illustrate right now. So because Qiskit has this way of working, you don't have to use just the built-in Qiskit sampler. You could use a sampler or an estimator from anywhere. So in this case, IBM is the only hardware at the moment which supports a primitives-based runtime. So if you're running on a real device using a primitive, you're probably going to be calling your IBM Qiskit runtime primitives. But for example, you could call like a specific sampler from the air simulator, or maybe you have your own quantum computer at home and you've implemented some form of primitives runtime on your own quantum computer and you want to use it with Qiskit. You can do that as well, just by importing the sampler from your provider. But then the process of kind of running it and getting your results, that is all Qiskit, and it's all kind of the same. I have a few examples here of how you can run it within Qiskit. This maybe is, as we're coming up to time, maybe you just want to have a look at this at home. But what I showed you here was just how you would run and get things resolved with the built-in kind of simulator within Qiskit. And this is the same version of doing that, but this time if I was calling the Qiskit runtime primitives themselves. If I wanted to run on real hardware using this primitives-based runtime execution model. I think this is maybe a good place to end. If you have some time in your own time, I also gave you a few examples of other packages you could use, like Qiskit experiments or Qiskit dynamics. But unfortunately, I think we just don't have enough time to go through that today. But yeah, thank you very much for your attention. Maybe we have like 2 minutes for questions, if there are any.
じゃあせっかくなんで、Abby, I have a quick question.
Yeah.
Yeah. So, do you have any event related to Qiskit event in the near future? So, do you have a plan?
Ooh, okay.
Yeah.
So
maybe you can advertise Qiskit event.
We have I don't know of any in-person events that are public-facing coming up at the moment, but when we do have events, we always publish them on .org/events. If you go to this page in our website, you can see some of the things that we have upcoming. A lot of them at the moment are still virtual. So every Friday we have a YouTube guest lecturer come and talk about normally some pretty advanced research topics. We also have demo days, which are publicly, they're open to the public. If you have built something in Qiskit, or you have a project that you've done with Qiskit, and you want to kind of give a demo of what you've done and get some feedback from IBMers, other Qiskit developers, definitely drop me a message and we can set that up. We have Qiskit office hours. This is if you're struggling with anything with Qiskit, particularly if you want to contribute to our open source ecosystem and you don't know how to get started, come along to those. There you have 2 or 3 Qiskit maintainers available to help you out. Yeah, those are the most, those are the key ones that I know of and involved in. But yeah, there's plenty of other things on this page that maybe yeah, go and have a look and see if there's ones happening in your region or online. Things that I think starting to ramp up a bit more now that kind of COVID is things are a little bit easier to do now. But yeah, thank you for the question.
Yeah, thank you very much. I have another quick
Yes,
question.
please,
So,
go
do you
ahead.
have any information about this year's Qiskit Advocate nomination?
Yes, actually, that is, yes, very good segue. I have, at the end of this notebook, there is like a lot of different information. One of them is the Qiskit Advocates Program. If you are really passionate about Qiskit, if you have made a lot of contributions to the community, that could be making pull requests to Qiskit. Qiskit is all open source, so anyone can come along and contribute to it. Or if you have organized events at your, I don't know, at your school, or if you have written blogs or done live streams coding with Qiskit, if you have kind of given back to the community, we really want to support you. And to do that, you can apply to become a Qiskit advocate. Applications open every June or July. Keep an eye out on our Qiskit social channels for when that's happening. There's a link here where you can see an application guide, everything you need to do to prepare for that application. And once you join the Qiskit advocates, then you kind of you get to kind of join this very cool club of other advocates who are passionate about Qiskit. You get to you know, have good networking opportunities, mentorship opportunities, and yeah, it's a really great opportunity. So definitely go and look into that.
Yeah, thank you for the information.